All right, I will be talking about the steps of depolarization, muscle contraction, and then the second part of this is heart failure and how imaging can help that. So, starting off strong, like everything else in cardiovascular physiology, we're gonna start with the heart, which looks like a big potato and has 4 chambers, which are right atrium, right ventricle, left atrium, and the left ventricle. All right, so for depolarization, you start with this SA node up here. That sends a signal through the heart like this. Now, the SA node creates signals by itself. It has like things that can speed it up, like your parasympathetic nervous system can slow it down through the vagus nerve, and the sympathetic nervous system can speed it up through the accelerator nerve, and it connects in 2 different places. But it has its own like rhythm, which is 100 beats per minute. And then the reason most people have, okay, I won't say most people, but healthy-ish people have heartbeats under 100 beats per minute is because your parasympathetic nervous system is the stronger one, and it slows it down because you're not doing that much stuff. You don't need to be doing 100 beats per minute. So the intercalated discs work like this. You have muscle cell and a muscle cell, and the signal is started at the SA node, and then it hits these ones, and then it hits these ones, and then it hits these ones, and it goes cell to cell like this. Woohoo! And then boom, crosses that bridge, and then to the next one, crosses that bridge. But this right here is a bunch of dead tissue. You can't get this signal all the way down here. That's why we have the AV node. And that splits into the right and left bundle of his, goes down the bundle branches and up the Purkinje fibers. It pushes, so this signal contracts or causes the contraction to go downwards, and this one causes the contraction to go upwards to get the left atrium to push it to be through the aorta and overcome all that back pressure from your arterial pressure and blood and body, all the stuff. And then this one, the right ventral, sends it out through the pulmonary artery. So, okay, and then for chicken stitch. For depolarization you can see on an EKG. Oh, there we go. Okay, yeah. So you have your P wave. This is atrial depolarization. Your QRS, which is ventricular depolarization, and this one's your bundle branches, and this is your Purkinje fibers. So it goes up your bundle branches and down your Purkinje fibers, and then you have your T wave, which is ventricular repolarization. So we already talked about the 4 chambers of the heart. So your SA node, that is your P wave. This is your SA node, the thing that starts it all. And then it goes across, and that's what makes your P wave is that signal traveling through your ventricle or your atriums. And it hits your AV node, and this is what's known as AV nodal delay. And then as soon as it hits your AV node, which is here, it goes up your bundle branches and down your Purkinje fibers. So down your bundle branches and up your Purkinje fibers, and squishes the heart, and that's QRS. And then you have ventricular depolarization. You have atrial depolarization, but that's overshadowed by this. ventricular repolarization is kind of just a relaxing of the ventricles, so that you can get ready for your next contraction, which is the SA node. And then I said the SA node depolarizes by itself. It doesn't really have a resting membrane, so it's continuous. It's kind of like woo, like that. AV node also has its own, but it's longer than the SA node. So if the SA node was to fail, you would still get that passive filling before AV node contracted by itself. But because SA node beats AV node to it, you get the SA node time, whatever that is. So for each individual cell during muscle contraction, we have this whale diagram, which is just one of the cells. So calcium comes in, picked up by the L-type receptors, taken across the feet, and given to the RER, which drop or like signal to the sarcoplasmic reticulum to release calcium. This calcium will then hold up, bind to troponin C, which will undo tropomyosin from actin, which allows the myosin heads to reach down, pick up actin, and then pull it back. And to pull it back, it drops phosphate 1, or just phosphate, and then it drops ADP. So then that's like 1, 2. And then ATP will reconnect to the myosin heads, release it, and reset it so it can do it multiple times with as much ATP. And then it phospholambin signals to SERCA when calcium needs to be re-vacuumed up into the sarcoplasmic reticulum. All right, so that's how we exert force in the heart and the muscle. This side is obviously stronger to push up, push the blood into the body and overcome aortic pressure. But if it gets too thick, then Frank Starling mechanism can't really work because it won't stretch, so then it can't squeeze, because Frank Starling is the bigger the stretch, the bigger the squeeze. So if this is so tight and condensed and muscular that it can't stretch enough to push, because it's if it can push really hard here, that's great, but if it can push from here, that would be better. But since it's so muscular, it can't. That's a type of heart failure. So going into heart failure,